Traditional radio systems are built around fixed hardware: one device, one frequency, one waveform. Software-defined radio replaces that constraint by moving signal processing into software, making the hardware reconfigurable by design. First, flexibility. A single hardware platform can support different waveforms, protocols, and frequency bands without physical modification. Second, programmability. Signal processing logic, protocol behavior, and test scenarios are all defined and modified in software. Third, reproducibility. Experiments can be repeated, verified, and extended by researchers and engineers on the same hardware platform. Modern electronic warfare, EW, demands adaptability. Our software-defined radio platform delivers 3 mission-critical capabilities from a single reconfigurable hardware system. These capabilities include live video transmission between drones and ground unit, drone detection system, and interference system using signal jamming. In our example, 2 SDRs are used to demonstrate air unit system for video signal transmission and receiving side on the ground unit. These tests demonstrate the capabilities of PhilPal-designed BTOF and BTOZ SDR. BTOF and BTOZ are designed to be a single channel and dual channel with half or full duplex configurations, respectively. To dive deeper into the transmission pipeline, video signal is first wrapped into transport stream from drone camera. The stream is then linked to SDR for packet encoding and modulation before being transmitted from transmit port, which is then received on the receiving port of the SDR on the ground unit. In order to display video output, the receiving signal needs to be demodulated. Both the transmit and receive pipelines are observable in real time. Pipeline state and stream timestamps are logged directly in the terminal. The GNU radio frequency sync confirms the spectral shape and occupied bandwidth of the received signal. Since all signal processing is implemented in software, encoding parameters such as resolution, bitrate, and latency can be modified and redeployed without any hardware chain. In real application scenarios, transmission is done by mounting SDR to the drone, completing the air unit. This also introduces the capability of creating a mesh network, allowing multiple drones to communicate via video and extending transmission range to a single ground unit monitor. The system architecture consists of 2 independent SDR units operating on a single host machine. The first is a communication and signal detection chain, where an incoming RF signal is captured, processed, and decoded. The second is an interference chain, where a separate SDR transmits a targeted jamming signal based on operator input. These 2 chains share the same host but have no direct RF feedback path between them. On the hardware side, a receive-only SDR is used as a detection module with a dedicated detection antenna, connected to the host over Ethernet. This setup is paired with a high-output power SDR with a transmit antenna, also connected to the host via gigabit Ethernet. Both units are driven entirely from software on the same machine. With PhilPal DJI Decode Plus, drone signal is detected and decoded from the proprietary protocol library stored onboard, enabling offline decoding of known drone signals without any network dependency. Jamming signal is transmitted via NTOZ with interchangeable daughterboard architecture. Configuration allows up to 20 dBm of output power across the target frequency bands. Our drone detection and decoding capability implements both offline protocol decoding and in-house AI classification technique to tag and label drone signals. These 2 techniques are developed to allow for detection and classification of both known and unknown drones. Stored library protocol decoding are mainly made of common-of-the-shelf (COTS) drone from commercial suppliers. Each of these drone typically operates at 2.4 and 5.8 GHz with proprietary RF communications protocols such as ARSDK for Parrot, Skylink for Autel, and OcuSync for DJI. DIY drones typically operate at lower frequency bands such as 433 MHz and 915 MHz using Mavlink or custom protocol. This limits the capability for drone detection due to the nature of the drone itself. PhilPal YOLO models are developed to combat this by introducing ALML to label RF signals from different sources, such as RC, DIY drones, and published IQ data. During live detection, our UI are able to distinguish between drone decoding using offline library and AI classification. With SDR flexibility, jamming waveform creation can be controlled to transmit various jamming techniques. This is particularly important to combat drones with anti-jamming safety, such as frequency hopping spectrum, and in the case where precise signal jamming needs to be carried out due to potential disruption of other signals in urban areas. Once the operating frequency of the drone is identified, the data can be linked to the jamming SDR to disrupt the communication link between the drone and controller. This allows for precise jamming without disrupting public signals. One SDR platform. 3 mission-critical capabilities. Infinitely adaptable through software for any operational requirement. Decode, detect, dominate.